Something is pushing the universe apart, and we do not know what it is. Welcome to the Sleepy Lab. Tonight, you will drift through one of the quietest and most profound mysteries in all of science. The story of how we discovered that something invisible fills all of space, and how that something is slowly, gently, irrevocably pulling the cosmos apart. If this kind of quiet wonder helps you sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. The year was 1998. Two teams of astronomers were doing something that sounds almost ordinary. They were measuring the brightness of distant explosions, the deaths of stars, far across the universe. These explosions are called Type Ia supernovae, and they have a remarkable property. When a certain kind of star reaches a critical mass and collapses, it detonates with almost exactly the same intrinsic brightness every time. Not approximately the same, nearly identical. This makes them useful in a very specific way. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it must be. The dimmer it looks, the farther it is. Astronomers call objects like this standard candles, reliable, consistent, measurable. The two teams in 1998 were using these supernovae as rulers, measuring the universe's expansion, checking whether gravity was doing what everyone expected, slowing things down, pulling the cosmos gently back toward itself. What they found was something else entirely. The supernovae were dimmer than they should have been. Not by a little, by enough to matter. Dimmer meant farther, and farther meant the universe had expanded more than any model predicted. The galaxies hosting those explosions had been carried away faster than gravity could account for. The universe was not slowing down. It was speeding up. Both teams arrived at this conclusion independently. Two groups of scientists, working separately, competing with each other, and both arriving at the same unsettling answer. The expansion of the universe is accelerating. There was no easy way to dismiss it. The data from one team might be questioned, but when a second team, using different instruments and different methods, finds the same thing, the result becomes very difficult to set aside. In 2011, the Nobel Prize in Physics was awarded to the leaders of both teams. A recognition that what they had found was not an error, not an artifact, not a misreading of the sky. It was real. The universe is expanding faster and faster, and something is responsible. That something was given a name: dark energy. It is worth pausing on that name for a moment. It is not a description, it is not an explanation. It is a placeholder, a label placed over a gap in our understanding. The way you might mark an empty shelf with a note that says, "Something goes here." We named it before we understood it. In some ways, we still have not moved much beyond the name. What we do know is this. Dark energy makes up roughly 68% of the total energy content of the observable universe. Not 68% of the matter. Of everything. Matter, radiation. All forms of energy combined. Nearly 7/10 of everything that exists, in the sense that physicists mean when they say exists, is this thing we cannot see, cannot touch, and cannot fully explain. Dark matter accounts for about 27%, and ordinary matter, the atoms, the stars, the planets, the oceans, the dust. Every galaxy you have ever seen in a photograph accounts for less than 5%. Less than 5%. Everything visible. Everything we have ever studied, named, or touched. A thin layer of familiarity over a universe that is mostly something else. It is important to say clearly that dark energy and dark matter are not the same thing. They share the word dark, and that is nearly all they share. They are entirely distinct phenomena, with different properties and different effects on the cosmos. Dark matter pulls. It is invisible, but it has gravity. It gathers around galaxies, holding them together, bending light as it passes. Without dark matter, galaxies as we know them would not exist. the stars would fly apart. Dark matter is a kind of invisible scaffolding, and gravity is how it makes itself known. Dark energy does something different. It does not pull, it does not gather, it does not hold anything together. It pushes space itself apart. And it does so everywhere, equally, without preference. Dark energy does not clump around galaxies or concentrate in any region. As far as we can tell, it is spread perfectly uniformly throughout all of space. Every cubic meter of the void between galaxies, every quiet corner of the universe, holds the same faint, steady presence of dark energy. It has no gravitational attraction toward any object. It does not draw anything closer. It does not interact with matter in any way we can directly measure. It simply persists, filling space. And as space grows, as the universe expands, dark energy does not dilute. It does not thin out the way matter does when spread across a larger volume. It remains constant, steady, quietly dominant. This is what makes it so strange. Matter, as the universe expands, becomes less dense. The same amount of matter spread across a larger space means less matter per cubic meter. Radiation dilutes even faster, but dark energy, if the simplest models are correct, maintains the same density no matter how large the universe becomes. And so, as the universe grows, dark energy's share of the total grows with it. It has been growing for billions of years. Roughly 5 billion years ago, it crossed a threshold. Its influence became stronger than gravity's ability to slow the expansion. And since that moment, the universe has been accelerating, not slowing towards some eventual stillness. Accelerating, pulling apart, growing faster. Two teams of astronomers, measuring the faint light of dying stars, found the edge of that threshold written in the data. And the universe has not been the same since. Somewhere out there, right now, a galaxy that was once within reach is crossing a horizon. Moving away from us faster than light can cross the distance, not because it is moving through space, but because space itself is stretching between us. It will never be reachable again. It will fade, redden, and vanish, not destroyed, simply gone from our sky. Dark energy is doing that, quietly, continuously, without announcement. And we have given it a name. That is where we are. Rest in that for a moment. The universe is 68% something we do not understand, and it is that something, that quiet, uniform, invisible presence, that is shaping the long future of everything. The simplest way to describe dark energy mathematically is also, in a way, the oldest. It is a symbol, a single Greek letter, lambda, written into the equations of general relativity more than a century ago. Einstein placed it there in 1917. At that time, the universe was believed to be eternal and still, not expanding, not contracting, simply existing as it always had, as it always would. The idea that space itself might be moving was not yet part of anyone's thinking. The cosmos was a fixed stage, and the stars were its permanent furniture. But Einstein's equations, when he first wrote them down, would not cooperate. Without modification, they described a universe that could not hold still. Gravity would pull everything inward. The cosmos would collapse. And so, to prevent that, to make the mathematics agree with what everyone assumed to be true, Einstein introduced a term, a counterbalance, a gentle repulsion built into the fabric of space itself, just strong enough to hold the universe in place. He called it the cosmological constant, lambda. For a few years, it seemed to work. The equations described a static universe. The physics community was satisfied, and Einstein moved on to other questions. Then, in 1929, Edwin Hubble published his measurements of distant galaxies. They were moving away from us, all of them, in every direction. The universe was not still. It was expanding, carrying galaxies apart, like marks on the surface of a slowly inflating sphere. The cosmos had never been static. It had been moving all along. Einstein, upon learning this, reportedly called the cosmological constant his greatest mistake. He had invented a term to solve a problem that did not exist. The universe did not need to be held in place. It was already in motion. Lambda was removed from the equations, set aside, and for decades, it was largely forgotten. A historical footnote, an embarrassment, a correction that turned out to be unnecessary. The physics community moved on, and Lambda sat quietly in the margins of old papers, waiting. It waited for 69 years. Then, in 1998, the supernova data arrived. Two teams of astronomers, working independently, found that the universe's expansion was not slowing down. It was speeding up. Something was pushing space apart. Something uniform. Something invisible. Something that behaved almost exactly like a fixed energy density spread evenly through all of space. Something that behaved, in other words, almost exactly like lambda. The cosmological constant was not a mistake after all, or rather, it had been introduced for the wrong reason, abandoned for the right one, and then resurrected by evidence that no one had anticipated. Einstein had stumbled onto something real without knowing what it was. Lambda is now the central term in what cosmologists call the lambda CDM model, the standard model of cosmology. Lambda stands for dark energy. CDM stands for cold dark matter. Together, they form the framework that describes the universe's large-scale structure with a precision that is, quietly, remarkable. The distribution of galaxies across hundreds of millions of light years, the faint temperature patterns in the oldest light in the universe, the way matter clusters into filaments and walls, and vast, empty voids. Lambda CDM predicts all of it, and the predictions hold. It is the best description of the cosmos we have. And at its heart is a term that assigns a fixed energy density to empty space itself. This is what the cosmological constant actually says, that the vacuum, the absence of everything, the space between particles, the void between galaxies, is not truly empty. It carries energy, a small amount, but a real amount, spread uniformly through every cubic meter of space in the universe. This property is called vacuum energy. And here is where the story becomes strange. Quantum field theory, the framework that describes particles and forces at the smallest scales, also predicts that empty space should carry energy. Virtual particles, flickering in and out of existence, too brief to observe directly, but real enough to affect the equations. The vacuum, in quantum theory, is not a passive backdrop. It hums with activity. It has energy. So far, the two pictures seem to agree. But when physicists calculate how much energy the quantum vacuum should contain and compare that number to the dark energy density we actually observe, the agreement collapses entirely. The theoretical prediction is larger than the observed value by a factor of roughly 10 to the power of 120. That is not a small discrepancy. It is not a rounding error or a missing decimal place. It is a number so vast that it is almost impossible to hold in the mind. A 1 followed by 120 zeros. The prediction and the observation are separated by more orders of magnitude than there are atoms in the observable universe. This gap has been called, with quiet understatement, the worst prediction in the history of physics. And it is not a failure of careless work. It is the result of two of our most successful theories, quantum field theory and general relativity, being applied together and producing an answer that is catastrophically, almost absurdly wrong. Something is canceling almost all of that theoretical vacuum energy. Something is leaving only the tiniest residue, the small, smooth, persistent value we call the cosmological constant. We do not know what that something is. We do not know if it is a single mechanism or many. We do not know if the cancellation is exact or approximate, permanent or temporary. We only know that it happened, and that the value left behind, that almost nothing, that whisper of energy in every cubic meter of space, is precisely the value that allowed the universe to form galaxies, and stars, and everything that followed. If the cancellation had been slightly less complete, dark energy would have been stronger. The universe would have expanded too quickly for gravity to gather matter into structures. There would be no galaxies, no stars, no slow accumulation of heavier elements in stellar cores, no planets forming from the debris of ancient explosions. If the cancellation had been slightly more complete, if lambda were zero or negative, the universe might have collapsed long before any of that could happen. The value we observe sits in a narrow corridor between those two outcomes, not because anyone arranged it, not because we know why, simply because that is what the data shows. Lambda is what it is. And what it is just enough. Rest with that for a moment. A symbol Einstein wrote down to solve the wrong problem. Abandoned, forgotten, resurrected by the light of dying stars. Now sitting at the center of our best description of the cosmos, a fixed energy density in the vacuum, a number that quantum theory cannot explain, a value so precisely tuned that its existence borders on the inexplicable. We have a name for it. We have equations that use it. We do not know what it is. And so the question remains, not just unanswered, but perhaps unapproachable with the tools we currently have. The cosmological constant problem, why the vacuum energy we observe is so vanishingly small compared to what quantum theory predicts, sits at the intersection of our two greatest theories of nature, and neither theory, on its own, can resolve it. Quantum field theory describes the very small with extraordinary precision. General relativity describes the very large with equal precision. But when you ask them both the same question, how much energy does empty space contain, they give answers that differ by a factor of 10 raised to the power of 120. That is not a rounding error. That is the largest discrepancy between theory and observation in the history of science. Some physicists believe there must be a cancellation mechanism, some deep symmetry in nature that causes the enormous theoretical vacuum energy to nearly cancel itself out, leaving only the tiny residue we observe, a kind of cosmic subtraction, precise to more than 100 decimal places. We have not found this mechanism. We do not know if it exists. But the alternative, that there is no mechanism, that the number is simply what it is, feels, to many physicists, like an answer that explains nothing. Others have taken a different path. Perhaps the cosmological constant is not truly constant. Perhaps what we call lambda is not a fixed property of space, but something that moves slowly, imperceptibly, over billions of years. A value that was different when the universe was young and will be different again when the universe is old. This possibility is taken seriously. It has a formal language. Dark energy that changes over time is described by a parameter called the equation of state, written simply as W. It is a ratio, pressure divided by energy density. For the cosmological constant, that ratio is exactly -1. Perfectly uniform, perfectly unchanging. A straight line drawn across all of cosmic time. If W equals -1, dark energy is what Einstein's lambda always was, a fixed energy woven into the fabric of space. The same yesterday as today, the same today as 1 trillion years from now. Current observations place West very close to that value. Measurements from supernovae, from the cosmic microwave background, from the distribution of galaxies across hundreds of millions of light years, all of them point toward -1. All of them are consistent with the simplest answer. But small deviations cannot yet be ruled out. The measurements are precise, but not infinitely so. There is still room within the data for W to be something other than exactly -1. A little more, a little less. Enough to change everything. One class of models lives in that space of possibility. They gather under the name quintessence, a hypothetical scalar field, something like a very slow wave moving through all of space, carrying energy that evolves over time rather than remaining fixed. Quintessence would not be dramatic. It would not announce itself. It would simply drift over billions of years across the entire universe, its strength shifting so gradually that no single observation could catch it moving. The dark energy of a billion years ago might have been slightly different from the dark energy of today. The dark energy of a billion years from now might be different still. If quintessence is real, the universe's fate is not written. It depends on how that field evolves, whether it strengthens or weakens, whether it eventually settles into stillness or continues to change. We do not have that answer. The field, if it exists, has not revealed its trajectory. There is something quietly humbling about that. The force shaping the entire future of the cosmos may be a field we cannot detect, evolving according to rules we have not yet found toward an outcome we cannot predict. And then there is a darker possibility, a model called phantom energy. In this scenario, W is not -1. It is less than -1. A small difference in a single number, and yet the consequences are unlike anything else in cosmology. Phantom energy would not remain constant. It would grow. Slowly at first, then faster, accumulating strength as the universe expands, feeding on the very expansion it drives. Unlike ordinary dark energy, which maintains a steady density as space grows, phantom energy becomes denser as space stretches. More space means more phantom energy. More phantom energy means faster expansion. Faster expansion means more space. A feedback loop, building without limit. The endpoint of this process has a name, the Big Rip. In the Big Rip, the expansion of space does not merely continue. It accelerates without bound, growing faster and faster until the force of expansion overwhelms every other force in the universe. One by one, the structures that gravity has spent billions of years assembling would come undone. The largest structures would go first. Galaxy clusters, vast collections of hundreds or thousands of galaxies, bound together across millions of light years, would find their gravitational bonds stretched beyond breaking. The space between their members would grow faster than gravity could hold them. They would dissolve, quietly, into the expanding dark. Then individual galaxies. Then solar systems, their planets drifting away from their stars as the space between them grows too fast for gravity to bridge. Then planets themselves, their surfaces pulled apart as the expansion reaches down to smaller and smaller scales. Then molecules, then atoms. The electrons of every atom in the universe would be stripped away as space expanded faster than the electromagnetic force could hold them together. In the final moments before the Big Rip, even atomic nuclei would be torn apart, the strong nuclear force, the most powerful force in nature, overwhelmed by the geometry of space itself. And then, nothing. Or rather, a universe of disconnected, structureless particles, each one alone in an expanding void, forever beyond the reach of every other. This is a hypothesis, not a prediction. The current data does not require it. W may be exactly -1. Phantom energy may not exist. The Big Rip may be a mathematical possibility that nature never chose to use. But it cannot be ruled out. The measurements that place W near -1 still leave room at the edges of their uncertainty for something less, something that grows, something that ends in that final, silent unraveling. It is worth sitting with the range of possibilities for a moment. On one end, a cosmological constant, space quietly humming with a fixed energy, forever, the universe drifting into cold and darkness over trillions of years. On the other end, phantom energy, a growing force that eventually tears apart every structure in existence, down to the last nucleus of the last atom. Between those two futures lies the number W, a single parameter, measured to be close to -1, not yet known to be exactly -1. The difference between a universe that fades and a universe that tears may be smaller than our current instruments can resolve. And so the telescopes keep watching, the surveys keep mapping, the data keeps accumulating, slowly narrowing the range of what W can be slowly closing in on an answer that may take decades more to reach. For now, the universe holds its future quietly, expanding in all directions, at a rate that has been accelerating for 5 billion years, driven by something we have named but not understood. Whether that something is fixed or moving, stable or growing, eternal or building toward an end, we do not yet know. We are listening for the answer in the light of distant galaxies. And the universe, as always, takes its time. If phantom energy is real, if W is truly less than -1, then the sequence of endings has a particular order. Galaxy clusters would go first. The gravitational bonds holding thousands of galaxies together, bonds that have persisted for billions of years, would simply be overcome, not broken violently, just loosened, the way a knot loosens when the rope is pulled slowly from both ends. The space between galaxies would grow faster than gravity could compensate, and the clusters would dissolve into their individual members, each galaxy drifting away from the others with no possibility of return. Then, the galaxies themselves. The stars within them, spread across hundreds of thousands of light years, would find the distances between them growing. The spiral arms would unwind. The structure would disperse, each star continuing on its own path, no longer part of anything larger. Then, solar systems. The planets, held in their orbits by the gravity of their stars, would find those orbits widening, then failing. The distances that have remained stable for billions of years would begin to grow, slowly at first, then faster. Then the planets themselves. The rock and iron and ice that make up a world held together by its own gravity would find that gravity insufficient. The surface would lift away, the interior would follow. A planet, in the end, is just matter that has agreed to stay close, and in the final stages of phantom energy domination, that agreement would be revoked. And then, at the very end, the atoms, the electromagnetic force binding electrons to nuclei, the strong nuclear force holding protons and neutrons together, these forces, which have operated unchanged since the first minutes of the universe, would be overwhelmed by the expansion of space itself. The last structures in existence would come apart at the smallest possible scale. This is the Big Rip. Not an explosion, not a collapse. A tearing, gradual, then total, working its way down from the largest scales to the smallest, until nothing composite remains. The estimated time to this endpoint, if phantom energy is real, is roughly 20 billion years from now. 20 billion years. A number large enough to feel abstract, and yet the universe is already 13.8 billion years old. On cosmic timescales, 20 billion years is not an eternity. It is an afternoon. But it is worth holding this gently. The Big Rip is a hypothesis. The data does not require it. Current measurements place west very close to -1, and a value of exactly -1. The cosmological constant would mean the Big Rip never happens at all. The scenario exists at the edge of what our instruments can distinguish. It is a possibility, not a verdict. The gentler fate, the one consistent with the true cosmological constant, has a different name. The Big Freeze, sometimes called heat death. In this version, nothing tears. Everything simply continues. Galaxies drift apart over trillions of years, carried by the same quiet expansion that is already underway. The distances grow. The light from distant galaxies redshifts further and further, stretching toward wavelengths too long to carry useful energy. One by one, the galaxies beyond our local group pass beyond the reach of any signal we could send or receive. The stars burn on for a while. The most massive ones exhaust their fuel in millions of years. The smaller ones, the red dwarfs, burn so slowly and so dimly that they will persist for trillions of years, 100 times the current age of the universe. But eventually, they too will exhaust their hydrogen. The last star will cool. The last ember will fade. What remains will be black holes. And black holes, as Stephen Hawking showed, are not truly permanent. They radiate energy slowly, imperceptibly slowly, losing mass over timescales so vast, they make the current age of the universe seem like a single breath. A stellar mass black hole might take 10 to the power of 67 years to evaporate. A supermassive black hole, 10 to the power of 100 years, or more. But eventually, even those will be gone. And the cosmos will approach what physicists call maximum entropy, a state in which energy is distributed so evenly, so uniformly that no further work can be done. No gradients, no flows, no processes. A universe that is not dead so much as finished, arrived at its final, most probable state. This is the long, quiet ending that a cosmological constant implies. Not a tear, a fade. And while all of this unfolds, across timescales almost impossible to hold in the mind, the observable universe continues to expand right now, in this moment, as you lie here. It is currently about 93 billion light-years across. That number surprises many people. The universe is 13.8 billion years old. So how can it be 93 billion light-years in diameter? The answer is that space itself has been expanding the entire time. Light that left the earliest galaxies 13 billion years ago has been traveling through space that was itself stretching, so the sources of that light are now much farther away than the light's travel time would suggest. And the boundary of what we can observe is itself moving outward. But here is the quiet strangeness at the heart of it. Because space expands, distant galaxies are not simply moving through space away from us. Space itself is growing between us and them. And beyond a certain distance, called the Hubble horizon, that growth is fast enough that the space between us and a galaxy is increasing faster than light can cross it. This does not violate relativity. Relativity says nothing can move through space faster than light. It says nothing about space itself expanding. The galaxies beyond the Hubble horizon are not breaking any law. They are simply being carried away by the geometry of the universe, receding at rates that no signal from us could ever match. And over time, dark energy will push more and more galaxies past that horizon. Galaxies that are visible to us today will, over billions of years, redshift beyond detection. Their light will stretch until it carries no information we can use. They will not disappear. They will simply become unreachable, permanently beyond the boundary of what any observer in our location could ever see or contact. In roughly 2 trillion years, the Milky Way and the small collection of galaxies gravitationally bound to it, the local group, may be the only visible structure remaining in the sky. 2 trillion years from now, an observer looking outward from any planet in our galaxy would see nothing. Not darkness in the way we mean it now, with stars and galaxies hidden behind clouds of dust, true emptiness. A sky with no external light sources, no distant smudges of other galaxies, no evidence that anything exists beyond the local group at all. And here is perhaps the most quietly unsettling thought in all of cosmology. A civilization arising in that distant era, if such a thing is possible, would have no way of knowing what we know now. They would observe a universe that appears static and isolated. They would have no evidence of expansion, because everything that could show them expansion would have long since receded beyond their horizon. They might conclude, as scientists once did before Hubble, that the universe is simply this: fixed, finite, alone. All the evidence we have gathered, the redshifts, the supernovae, the cosmic microwave background, the large-scale structure, would be gone from their sky. The universe will have hidden its own history, and they would have no way of knowing what had been there, what had been seen, what had been understood in this brief, early era when the cosmos was still young enough to be legible. We are living in that era now. We are living in that era now. And so, while we still can, while the sky is still full of evidence, it is worth pausing to consider what we have actually learned. One of the most remarkable things we have ever done is read the oldest light in the universe. It is called the cosmic microwave background, the afterglow of the Big Bang itself, a faint glow of microwave radiation that fills the entire sky, arriving from every direction at once, carrying information from a time when the universe was less than 400,000 years old. It is not visible to the naked eye, but mapped with sensitive instruments. It reveals a sky covered in the faintest variations, patches of light that are almost imperceptibly warmer or cooler than their neighbors. The differences are tiny, a few hundred thousandths of a degree, and yet those tiny fluctuations encode almost everything we know about what the universe is made of. They encode the density of ordinary matter, the density of dark matter, and the density of dark energy. All of it written in the temperature of ancient light. A satellite called Planck spent years mapping these fluctuations with extraordinary care. It measured the cosmic microwave background across the entire sky, building the most detailed portrait of the early universe ever assembled. And when the data was analyzed, when the patterns were compared against the predictions of every model, the answer came back clearly. Roughly 68% of the universe's total energy content is dark energy. Not 50%, not 90%. 68. The Planck satellite did not discover dark energy, but it confirmed, with quiet precision, how much of the universe we cannot explain. There is another way the early universe left its mark on the sky. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma, a sea of particles and radiation so tightly coupled that sound waves moved through it. Actual pressure waves, rippling outward through the infant cosmos. When the universe cooled enough for atoms to form, those waves froze in place. They stopped mid-ripple, and their pattern was imprinted on the distribution of matter across the universe. Today, billions of years later, that frozen pattern is still visible. Galaxies are not distributed randomly. There is a subtle preference, a slight excess of galaxy pairs separated by a particular distance, roughly 500 million light-years. This is called baryon acoustic oscillation. It is the echo of a sound wave that rang through the universe before a single star had formed. And because that distance was set by known physics in the early universe, it serves as a kind of ruler, a standard length stretched and scaled by the expansion of space over billions of years. By measuring how that ruler appears at different distances, at different moments in cosmic history, astronomers can trace how the expansion rate has changed. They can see, directly, the moment when dark energy began to take over, the slow transition from a universe decelerating under gravity to one accelerating under something else entirely. The baryon acoustic oscillation signal has been measured in survey after survey. Each time, it tells the same quiet story. There is also a subtler method, one that uses the shapes of galaxies themselves as a kind of instrument. Light does not travel in perfectly straight lines through the universe. It bends around concentrations of mass. The gravity of large structures, clusters, filaments, the great walls of the cosmic web, curves the paths of photons passing nearby. This means that when we look at distant galaxies, their shapes are very slightly distorted, stretched and sheared by the matter between us and them. The distortions are small. Individually, they are invisible. Any single galaxy might simply be elongated by chance. But across millions of galaxies, a coherent pattern emerges, a statistical whisper of the matter distribution between here and the edge of the observable universe. This is called weak gravitational lensing. And it too, carries the signature of dark energy, because the way structure grows, the way matter clusters and filaments form, depends on the balance between gravity pulling inward and dark energy pushing outward. The Dark Energy Survey spent years mapping this signal across hundreds of millions of galaxies. It covered a large portion of the southern sky, building a statistical portrait of how dark energy has shaped the universe's structure over time. The results were consistent with the cosmological constant. Dark energy, as far as the survey could tell, has not changed. But the measurements were not precise enough to be certain. And so, the work continues. A telescope called Euclid was launched in 2023. It is designed specifically for this purpose, to map the geometry of the universe across cosmic history, tracing the influence of dark energy from the present back toward the distant past. It will measure the shapes of billions of galaxies. It will map baryon acoustic oscillations across a volume of space larger than any previous survey. It will build the most detailed picture yet of how dark energy has behaved over the universe's 13.8 billion years. And alongside it, the Nancy Grace Roman Space Telescope will survey billions more galaxies, tracking supernovae and measuring the expansion history with a precision that was unimaginable a generation ago. These instruments are not searching for dark energy in the way you might search for a lost object. They cannot point at it, or catch it, or weigh it directly. They are searching for its fingerprints, the subtle ways it has bent the universe's history away from what gravity alone would have produced. The central question all of these surveys are trying to answer is deceptively simple. Is dark energy constant? Or has it changed? If it is truly constant, if the cosmological constant is exactly right, then the universe has a fixed, unchanging energy density woven into the fabric of space itself. And the mystery is why that density has the precise value it does. If it has changed, if dark energy was stronger or weaker in the past, then it is something more dynamic, a field, perhaps slowly evolving, and the mystery deepens in a different direction. Current data cannot yet distinguish between these possibilities with certainty. The equation of state, the parameter that describes dark energy's behavior, is consistent with -1, but small deviations remain possible. And there is another tension in the data that may be pointing towards something new. The Hubble constant is the number that describes how fast the universe is currently expanding, roughly 70 kilometers per second for every megaparsec of distance, meaning that for every 3.26 million light-years between 2 points, those points are moving apart at about 70 kilometers every second. But when astronomers measure this number using the cosmic microwave background, looking back to the early universe, they get a slightly different answer than when they measure it using nearby supernovae and variable stars. The two methods disagree, not by much, but by more than the uncertainty should allow. This is called the Hubble tension, and it has persisted for years, surviving improvements in both measurements. Some researchers have proposed that the answer lies in a form of dark energy that was active very early in the universe's history, before the first stars, before the first atoms, briefly accelerating expansion and then fading away. This early dark energy would have left a subtle imprint on the cosmic microwave background, shifting the predicted Hubble constant just enough to close the gap. The idea is speculative. It has not been confirmed, but it illustrates something important. Dark energy may not be a single, simple thing. It may have played different roles at different moments in cosmic history, present at the beginning in one form, dormant for billions of years, and then rising again to drive the acceleration we observe today. Or it may be exactly what the simplest model says it is, a fixed, featureless property of empty space, unchanged since the beginning, unchanged until the end. We do not yet know. And that not knowing is not a gap in the story. It is the story. Consider what it means for something to be small. Not small the way a stone is small, or a seed, but small in a way that almost escapes the language of numbers entirely. Dark energy's density, the amount of it present in any given region of space, is roughly 6 times 10 to the negative 27 kilograms per cubic meter. That figure is so close to zero that writing it out feels almost like writing nothing at all. To make it concrete, imagine a volume of space the size of the Earth, that vast sphere of rock and ocean and atmosphere, some 12,000 kilometers across. Fill it entirely with empty space, and the dark energy contained within that volume would weigh less than a single grain of sand. Less than a grain of sand. And yet, that almost nothing is enough to accelerate the entire universe. Because space is not a small thing. Space is incomprehensibly large, and it is everywhere, and every cubic meter of it carries that same quiet density. When you sum it across the observable universe, across 93 billion light-years of space in every direction, the total becomes a force that no gravity can overcome. The cumulative weight of almost nothing, repeated across everything, becomes the dominant fact of the cosmos. This is one of the stranger truths in all of physics, that the largest effect we know of arises from the smallest density we have ever measured. And it raises a question that physicists have sat with for decades without resolution. Why this value? Not why dark energy exists, that is a separate mystery, but why does it have precisely this density and not some other? If dark energy were even a few times stronger than it is, the universe would have expanded too quickly for gravity to gather matter into galaxies. The slight over-densities left over from the Big Bang, the seeds of everything that would become stars and planets, and, eventually, in-laws would have been pulled apart before they could grow. Space would have stretched faster than gravity could hold anything together. The universe would be vast and smooth and empty. No galaxies, no stars, no anything. And if dark energy were slightly weaker or absent entirely, the story goes the other way. Gravity, unopposed, would have continued pulling the universe inward. The expansion would have slowed, stopped, reversed. The cosmos might have recollapsed long before the first stars had time to ignite. Everything that exists would have been compressed back into a point, billions of years before any of it had a chance to become complex. The value we observe sits in a narrow corridor between these two outcomes, just strong enough to drive acceleration, just weak enough to have allowed galaxies to form first. This is what physicists mean when they speak of fine-tuning, not that someone adjusted a dial, but that the number, whatever its origin, happens to fall in the one range where the universe becomes interesting. And there is a second coincidence, quieter but equally strange. Matter and dark energy have very different histories. In the early universe, matter was dense, packed tightly into a hot, bright plasma. As the universe expanded, that matter spread out. Its density fell. It diluted, the way ink dilutes in water, growing fainter as the volume around it grew. Dark energy did not dilute. Its density stayed constant, the same amount per cubic meter, always, regardless of how large the universe became. These two quantities, matter density and dark energy density, have been evolving in completely different ways for 13.8 billion years. One falling steadily, one holding perfectly still. And yet, right now, at this particular moment in cosmic history, they are within a factor of roughly 2 of each other. Not equal, but close. Closer than they have any right to be, given how differently they behave. In the far past, matter was overwhelmingly dominant. Dark energy was negligible by comparison. In the far future, matter will have diluted almost to nothing, and dark energy will reign almost entirely alone. The window in which the two are remotely comparable is narrow, a few billion years, out of a history that stretches toward infinity. And we are living in that window. This is called the coincidence problem, and it is, in its quiet way, one of the most unsettling puzzles in cosmology. The probability of finding yourself in the brief era when matter density and dark energy density are within a factor of 2, if you were to pick a random moment in the universe's history, is extraordinarily small. And yet here we are. Some physicists have an answer for this, or at least a framework for thinking about it. The anthropic principle suggests that we should not be surprised to find ourselves in this particular era, because only in this era could we exist. In the distant past, when matter dominated completely, the universe was too young for stars to have lived and died and scattered the elements that make up living things. In the distant future, when dark energy dominates completely, the universe will be too cold and too empty for anything complex to persist. The window in which observers are possible is roughly the window in which matter and dark energy are comparable. So of course we find ourselves here. We could not find ourselves anywhere else. This reasoning has a certain elegance. It does not require a coincidence to be explained. It reframes the coincidence as a selection effect. We are not lucky to live in this era. We are simply the kind of thing that can only exist in this era. Looking back and noticing that the era suits us. But not everyone finds this satisfying. Some physicists feel that the anthropic argument, however logically valid, explains too little. It tells us why we observe the coincidence, but not why the coincidence exists in the first place. It shifts the question without answering it. And for those who believe that physics should ultimately explain why the universe has the properties it has, not merely why we happen to observe those properties, the anthropic principle feels like a door closing rather than one opening. These researchers look for something deeper, a dynamical reason why dark energy's density should naturally be comparable to matter density at the moment when observers arise. A mechanisms, not a selection. A cause, not a correlation. No such mechanism has been found. The coincidence problem remains open, sitting alongside the cosmological constant problem, alongside the question of what dark energy actually is, alongside the Hubble tension, a cluster of related mysteries, each one pointing at the same gap in our understanding. We have a number. We have measured it carefully. We know what it does to the universe. We do not know why it is what it is. And perhaps that is where the night should rest for a moment. On the strangeness of a universe that seems, in some quiet way, to have been arranged, not by intention, perhaps, but by some principle we have not yet named, a universe whose largest force is almost too small to measure, and yet precisely large enough for everything. One framework exists that tries to make sense of the coincidence, not by finding a mechanism, but by changing the question entirely. String theory, in its most expansive form, does not predict a single universe. It predicts a landscape, a vast collection of possible universes, each with its own physical constants, its own laws, its own value of the cosmological constant. Some of those universes would have a cosmological constant so large that space would tear itself apart before a single atom could form. Others would have a constant so negative that the universe would collapse inward in an instant. The landscape contains, by some estimates, something like 10 to the power of 500 distinct possibilities, a number so large it has no meaningful comparison. In this picture, different regions of a larger multiverse might each settle into a different corner of that landscape. Each one a universe unto itself, unreachable from any other. And we would naturally find ourselves in one of the rare regions where the constant is small enough, just small enough, for gravity to gather matter into galaxies, for galaxies to harbor stars, for stars to forge the elements that eventually, after billions of years, arrange themselves into something capable of asking questions. This is not a new idea. The physicist Steven Weinberg proposed this reasoning in 1987, more than a decade before the supernova teams made their discovery. He used the anthropic logic carefully, almost reluctantly, and arrived at a prediction. The cosmological constant, if it exists, should be small and positive, not zero, but small, just large enough to be consistent with the existence of observers, and no larger. When the 1998 data arrived, when the supernovae came back dimmer than expected, when the expansion turned out to be accelerating, Weinberg's prediction was confirmed. It was a rare thing, an anthropic argument that had made a testable forecast, and the forecast had held. And yet, the multiverse interpretation remains one of the most contested ideas in all of modern physics. Many researchers find it deeply unsatisfying, not because it is obviously wrong, but because it may be impossible to test. If the other regions of the landscape are forever beyond our horizon, forever unreachable, then their existence cannot be confirmed or refuted by any observation we could ever make. A theory that cannot be tested is, to many scientists, not quite a theory at all. It is a framework, a way of organizing the question, but not an answer in the way physics has traditionally meant the word. Others defend it. They point to Weinberg's prediction as evidence that the framework has real content. They argue that the discomfort with untestability reflects a philosophical preference, not a scientific one. The debate continues. quietly, in papers and conferences and late conversations, and no resolution is near. So the mystery remains where it was. And perhaps it is worth sitting with what that mystery actually means, not in the abstract, but in the concrete. Dark energy cannot be directly detected. This is not a limitation of current instruments, waiting to be overcome by a better telescope or a more sensitive detector. It is something more fundamental. Dark energy leaves no particle tracks in any detector. It emits no radiation across any wavelength. It absorbs no light, bends no beam, triggers no signal of any kind that any instrument has ever been designed to catch. Its existence is known entirely from its effect on the universe's expansion history, from the fact that distant supernovae are slightly too dim, from the way the cosmic microwave background curves, from the spacing of galaxies across hundreds of millions of light years. Dark energy is inferred, always inferred, never observed directly. This makes it unlike anything else we know. Even dark matter, which is also invisible, which also emits nothing, leaves traces that can be mapped. The stars at the edges of galaxies move too fast for the visible matter to explain. They orbit as though surrounded by an invisible halo of mass. That halo can be traced, its shape reconstructed, its density estimated. Dark matter interacts gravitationally in ways that leave a readable signature on the motion of stars and gas. Dark energy does not do this. It does not pull on individual objects. It does not alter the orbit of a planet or the rotation of a galaxy. Its effect is not local at all. It acts on the geometry of the universe itself, on the fabric of space, on the rate at which distances between unbound objects grow. It is a property of space, not a thing within space. This distinction matters. General relativity allows for substances with negative pressure. This sounds strange, and it is. In ordinary experience, pressure pushes outward. A gas in a container presses against its walls. Negative pressure would seem to mean the opposite, a kind of inward pull. But in the cosmological sense, negative pressure means something different. It means that as space expands, as the volume of the universe grows, the substance does work on that expansion. It contributes energy to the process of space stretching rather than resisting it. This is why dark energy accelerates expansion rather than slowing it. A substance with negative pressure spread uniformly through space does not fight the expansion of the universe. It feeds it. Each new cubic meter of space that comes into existence carries with it the same density of dark energy as before. The energy does not dilute. It does not thin out as the volume grows. It simply persists, constant, everywhere, always. And so, as matter and radiation slowly thin, as the universe grows larger and the density of ordinary things falls, dark energy becomes, by comparison, ever more dominant. Not because it grows stronger, but because everything else grows weaker. The ratio of -1, pressure to energy density, is what makes this possible. It is the mathematical signature of a substance that remains constant as space expands. A substance that is, in some sense, a property of space itself rather than something contained within it. Whether that substance is truly the cosmological constant, a fixed, eternal feature of the geometry of space-time, or whether it is something that evolves, something that will one day change, is a question the universe has not yet answered. What is certain is this: something fills the emptiness, something that cannot be seen, cannot be touched, cannot be detected by any instrument we have built. Something known only by the gap it creates between where things are and where they would be without it. It is the largest component of the universe. It shapes the fate of everything. And we do not know what it is. There is a quietness to that. Not the quietness of defeat, but the quietness of standing at the edge of something very large and simply looking. The universe has given us enough clues to know that something is there. It has not yet given us enough to know what. And so the instruments keep watching. The surveys keep mapping. The theorist keeps searching the landscape of equations for something that fits, while the universe, indifferent and vast, continues its long acceleration into the dark. And so the acceleration continues, not because something pushes from outside, but because of what space itself carries within it. There is a way to describe this mathematically, a single ratio that captures the strange nature of dark energy more precisely than any metaphor can. Physicists call it the equation of state. It is written simply as W, and it equals pressure divided by energy density. For dark energy, that ratio is approximately -1. -1, a number that seems small, almost unremarkable, and yet it contains everything unusual about dark energy's behavior. Ordinary substances have positive pressure. They push outward, and as they expand, they lose energy. A gas released into a larger volume cools and thins. Radiation spreading across a growing universe reddens and fades. Matter, as space stretches, becomes more dilute. The same number of particles spread across an ever larger volume. Dark energy does none of this. A ratio of -1 means that as the universe expands, dark energy's density does not change. The energy in each cubic meter of space remains the same, even as the universe grows. More space simply means more dark energy, not the same energy spread thinner, but genuinely more of it, keeping pace with the volume. This is what negative pressure means in the language of cosmology. Not a vacuum pulling inward, but a substance that does work as space expands, that replenishes itself as the volume grows, that resists dilution in a way nothing else in the universe does. And this is precisely why it accelerates expansion rather than resisting it. The more space there is, the more dark energy there is. The more dark energy there is, the faster space expands. The faster space expands, the more space there is. A quiet, self-sustaining process, running in the background of everything. For most of the universe's history, this process was hidden. In the early universe, matter was dense, radiation was dense. The gravitational pull of all that mass and energy was more than enough to slow the expansion that began at the Big Bang. Space was still growing, but reluctantly, pulled back by everything within it. There is a quantity cosmologists use to track this history. They call it the scale factor, a single number that describes how large the universe is at any given moment relative to its size today. As time passed in the matter-dominated era, the scale factor grew, but slowly, following a curve described as time raised to the power of 2/3, a steady, decelerating climb. Then, roughly 5 billion years ago, something shifted. Not suddenly, not with any signal that any observer could have noticed, but gradually, as the universe expanded and matter thinned, the balance between gravity and dark energy began to tip. Matter dilutes as space grows. Dark energy does not. So as the universe expanded, matter's share of the total energy budget shrank and dark energy's share grew, until, about 5 billion years ago, dark energy crossed the threshold. It became the dominant component of the universe's energy content, and the expansion, which had been slowing for 8 billion years, began to accelerate. The universe changed direction, not in space, in time, in the rate at which it was growing. A change not in velocity, but in acceleration. Physicists sometimes call this the cosmic jerk, a term borrowed from the mathematics of motion, where jerk describes a change in the rate of change of speed. The universe, in a sense, lurched from one regime into another. Before that moment, gravity was winning. After it, dark energy took over. And the scale factor, which had been climbing along that gentle 2/3 curve, shifted into a different kind of growth entirely. Exponential. In the dark, energy-dominated era, the scale factor does not just grow, it doubles, and doubles again, and doubles again, over a fixed interval of time. The distance between unbound objects, galaxies not held together by gravity, increases not by addition, but by multiplication. Each doubling carries things further than the last. This is a qualitatively different universe from the one that existed before. In a decelerating universe, distant things are always, in principle, catchable. Given enough time, light can cross the gap. In an exponentially expanding universe, the gap grows faster than light can close it. Objects that are far enough away today will never be reachable, no matter how long you wait. The universe has, in a sense, developed a horizon it cannot see past. And that horizon is shrinking, not in absolute terms, but in terms of what lies within it. More and more of the cosmos is being carried beyond the reach of any signal, any observation, any connection. There is something in this that echoes an earlier chapter of cosmic history. In the universe's first fraction of a second, a sliver of time so small it has no name in ordinary experience, space underwent a period of exponential expansion called inflation. In that brief moment, the universe grew by an enormous factor, smoothing out irregularities, stretching quantum fluctuations into the seeds of future galaxies. Inflation ended. The energy driving it decayed into the particles and radiation that filled the early universe, and the cosmos settled into its long, matter-dominated adolescence. What drives the current acceleration is almost certainly different from what drove inflation. The energy scales are separated by many orders of magnitude. Inflation was violent and brief. Dark energy is gentle and, as far as we can tell, without end. But both involve the same fundamental behavior. Space expanding faster than matter can keep up, geometry outrunning physics. Some cosmologists wonder whether the two are related, whether the scalar field that drove inflation left some faint residue, some echo in the structure of space, that we now observe as dark energy. It is a speculation, not a conclusion. The mathematics of inflation and the mathematics of dark energy share a family resemblance, but the connection, if any exists, remains hidden. What is not hidden is the evidence. Distant supernovae, those standard candles burning at known brightness across billions of light years, carry within their dimness the entire history of the universe's expansion. By measuring how far they are and how fast they are receding, astronomers reconstruct the scale factor's journey through time. They can see, written in the light of dying stars, the moment when deceleration gave way to acceleration, the moment dark energy took the wheel. It is a remarkable thing to read the universe's biography in the fading light of an explosion that happened before the Earth existed. And what that biography says is this: for most of its life, the universe was held together by gravity. Matter pulled on matter. Expansion slowed. The cosmos was, in some sense, still negotiating with itself about what it would become. Then dark energy crossed the threshold, and the negotiation ended. The universe chose acceleration, not because anything decided, but because the numbers, balanced as they are, made it inevitable. A density that does not dilute, a pressure that is negative, a ratio of exactly, or very nearly, -1. These are not dramatic quantities. They do not announce themselves. They simply persist, quietly, uniformly, in every cubic meter of space, in every direction, at every moment. And the universe, carrying this quiet constant within it, expands, doubling and doubling again into a future that grows larger with every breath you take. There is a thought that some cosmologists return to, quietly, when they consider what dark energy might be. It concerns the very beginning. In the universe's first fraction of a second, a span of time so brief it has no name in ordinary experience, space expanded at a rate that makes today's acceleration seem almost still. This was inflation, a period when the universe grew from something smaller than an atom to something larger than a galaxy, in less time than light takes to cross a proton. That expansion was driven, most likely, by a scalar field, a kind of energy woven into space itself, with no preferred direction, no center, no edge. It filled everything, pushed outward with enormous force, and then, abruptly, it ended. The field decayed, its energy converted into the first particles of matter and radiation, and the universe began the long, slower work of becoming what it is. Dark energy may be something like that field. Not the same. The energy scales are separated by many orders of magnitude. Inflation operated at energies so vast they are difficult even to write down. Dark energy's density is almost incomprehensibly small by comparison. They are not the same phenomenon. And yet, both involve space expanding faster than matter can keep up. Both appear to arise from something intrinsic to space itself, rather than from any object within it. Both are described, at least approximately, by scalar field mathematics. The structural resemblance is quiet, but persistent, and some cosmologists find it too suggestive to ignore. Perhaps the universe has a habit of doing this, of threading scalar fields through space, letting them drive expansion for a time. Inflation did it violently, briefly, and then released its energy into matter. Dark energy does it gently, endlessly, and shows no sign of releasing anything at all. As far as we can tell, it has simply persisted, unchanged, for 5 billion years. That persistence has left its mark on everything we see. The universe is not a smooth, uniform place. It is threaded with structure, vast filaments of galaxies stretching across hundreds of millions of light years, dense nodes where clusters gather, and between them, enormous empty regions called voids. This is the cosmic web, and it is one of the most beautiful, large-scale patterns in nature. It formed because matter is not perfectly uniform. In the early universe, tiny fluctuations in density, quantum ripples, stretched to cosmic scales by inflation, seeded the growth of structure. Gravity did the rest, pulling matter toward the denser regions, building filaments and clusters over billions of years. But dark energy was also present, shaping what gravity could and could not do. Without it, gravity would have continued its work uninterrupted. Matter would have kept falling inward. Clusters would have kept growing. The filaments would have thickened and merged. The cosmic web would look different, denser, more tangled, more compressed. Dark energy changed that roughly 5 billion years ago, as dark energy crossed the threshold and began to dominate the universe's energy budget. The growth of the largest structures slowed and then stopped. Galaxy clusters, the most massive gravitationally bound objects in the universe, ceased to accumulate significant new mass around that time. The expansion of space had grown strong enough to prevent matter from falling inward across the largest distances. The clusters that existed were, in a sense, frozen at their peak. This is not just a theoretical prediction. It has been confirmed by observation. Hot gas trapped within galaxy clusters emits X-rays. The temperature and distribution of that gas encodes the cluster's mass and history. By studying X-ray emissions from clusters at different distances, and therefore different points in cosmic time, astronomers have traced how cluster masses evolved. The data matches the lambda CDM prediction with quiet precision. Clusters stopped growing when dark energy said they should, and the voids grew. The empty regions between the filaments of the cosmic web are not simply the absence of matter. They are spaces that dark energy has been slowly enlarging for billions of years. Some of the largest voids span hundreds of millions of light years. They are among the biggest coherent structures in the observable universe, and they are still growing. As dark energy drives galaxies apart, the filaments thin, the clusters drift away from one another, and the voids between them deepen and widen. The cosmic web is not static. It is slowly unraveling at its largest scales, its grandest structures gently dissolving into the expanding space between them. This is happening slowly enough that no human lifetime, no civilization's history, could perceive it directly, but it is happening. And dark energy has left another mark, one written not in the positions of galaxies, but in the oldest light in the universe. The cosmic microwave background is the afterglow of the Big Bang, a faint glow of microwave radiation that fills the sky in every direction, carrying information about the universe as it was nearly 14 billion years ago. It is the most precisely measured thing in cosmology. And dark energy has touched even this. When photons from the cosmic microwave background travel through the universe, they pass through the large-scale structures of the cosmic web, through the gravitational wells of clusters and filaments, and through the vast emptiness of voids. As a photon falls into a gravitational well, it gains a little energy. As it climbs back out, it loses energy. In a universe without dark energy, these two effects cancel almost perfectly, and the photon emerges unchanged. But in a universe with dark energy, the gravitational well is not the same when the photon exits as when it entered. Dark energy has caused the well to shallow slightly during the photon's crossing. The photon gains a little more energy falling in than it loses climbing out. It arrives at our telescopes very slightly warmer than it would otherwise be. This is the integrated Sachs-Wolf effect. It is subtle, a temperature shift of perhaps a few millionths of a degree, and it cannot be seen by looking at the CMB alone. But it can be found by comparing CMB maps with maps of where galaxies actually are. Where there are more galaxies, there should be slightly warmer patches in the CMB. Where there are voids, slightly cooler ones. Astronomers have made this comparison. They have cross-correlated the CMB with galaxy surveys spanning hundreds of millions of light years, and the signal is there, faint, but present and consistent with a universe in which dark energy is real and active. It is, in its quiet way, one of the most elegant conformations in cosmology. A photon that traveled for billions of years, carrying within its temperature a tiny record of the gravitational landscape it crossed, a landscape shaped by something we cannot see, cannot touch, and do not fully understand. The universe leaves these traces everywhere if you know how to look. In the frozen masses of galaxy clusters, in the widening emptiness of voids, in the faint warmth of ancient photons, dark energy writes its signature, again and again, in a script we are only beginning to read. It does not announce itself. It simply persists, shaping, expanding, deepening the silence between things. And the universe, carrying this quiet constant within it, grows larger still. There is another way dark energy reveals itself. One that has nothing to do with light bending, or cluster counts, or the faint warmth of ancient photons. It has to do with time itself. The universe has an age, about 13.8 billion years. As best we can measure, that number is not arbitrary. It is a constraint, a boundary condition that any honest model of the cosmos must satisfy. And here is something worth sitting with quietly. If you remove dark energy from the equations, if you build a universe with only the matter we observe and let gravity do all the work, the numbers no longer add up. A universe governed by matter alone, with the density we measure, would be younger, significantly younger, too young, in fact, to contain the stars we can see. The oldest stars we know of live in globular clusters, ancient, tightly bound families of hundreds of thousands of stars, orbiting the outer edges of galaxies like the Milky Way. Some of these stars are roughly 13 billion years old. They have been burning, slowly and quietly, for nearly as long as the universe has existed. In a matter-only universe, there would not have been enough time for them. The universe would have arrived at its present state too quickly. The stars would be older than the cosmos that made them, which is, of course, impossible. Dark energy resolves this. By accelerating the expansion, dark energy stretches the timeline. It gives the universe more room, more duration. It makes 13.8 billion years possible. And in doing so, it makes those ancient stars possible too. It makes everything that followed them possible. There is something almost tender in that. The same force that is slowly pulling the cosmos apart was also, in a quieter way, the reason there was enough time for stars to form at all. Time is one way to read dark energy's presence. Distance is another. When light travels through expanding space, it stretches. The wavelength grows longer. Longer wavelengths shift toward the red end of the spectrum. This is called redshift. And the amount of redshift in a galaxy's light tells us how much space has expanded since that light began its journey. A small redshift means the galaxy is relatively nearby, and the light has not traveled far. A large redshift means the light left its source long ago, when the universe was younger and smaller, and has been stretching ever since. By measuring redshift alongside distance, by asking not just how fast the galaxy is receding, but how far away it actually is, astronomers can reconstruct the universe's expansion history. They can trace how fast space was growing at different moments across billions of years. This is painstaking work. It requires measuring thousands, then millions of galaxies, carefully, precisely, over years and decades. 2 surveys have done this with particular ambition. The first is called BOSS, the Baryon Oscillation Spectroscopic Survey. It mapped millions of galaxies across a wide swath of the sky, using the subtle patterns in their distribution to measure how dark energy has shaped expansion over time. Its successor is called DESI, the Dark Energy Spectroscopic Instrument, mounted on a telescope in the mountains of Arizona. It carries 5,000 tiny robotic fiber positioners, each one capable of capturing the spectrum of a single galaxy simultaneously, night after night. It gathers light from millions of distant sources, building the most detailed map of cosmic expansion ever attempted. In 2024, DESI released its first major results, and the data carried a whisper of something unexpected. A hint, not a confirmation, but a hint that dark energy may not be perfectly constant, that its strength may have shifted slightly over cosmic time, that the simple cosmological constant, the clean and elegant lambda that Einstein's equations allow, may not be the whole story. The signal is uncertain. The researchers themselves are careful to say so. It may be a statistical fluctuation. It may reflect some subtle error in the measurements. More data will be needed before any conclusion can be drawn. But the possibility is there, quiet and patient, waiting to be resolved. If it holds, if future observations confirm that dark energy has evolved, the implications would be profound. A cosmological constant does not change. By definition, it is fixed. If dark energy has changed, then it is not a constant. It is something else, something dynamic, something that has a history and perhaps a future that differs from its past. That would rule out the simplest explanation, and it would demand a new framework, new mathematics, new concepts, new ways of thinking about what empty space actually is and what it carries within it. The field of observational cosmology holds this possibility with a kind of quiet anticipation. Not urgency, not alarm, just the careful, sustained attention of people who know they may be standing at the edge of something important, and who are willing to wait for the universe to speak more clearly. There is one more thread worth following before rest. Some physicists approach dark energy from a different direction entirely. They do not ask what new substance might be filling space. They ask instead whether space itself, and the gravity that shapes it, might simply behave differently than we think on the largest scales. General relativity has been tested with extraordinary precision. In the solar system, in binary pulsars, in the ripples of gravitational waves. It holds, again and again, to remarkable accuracy. But those tests all occur on relatively small scales. The scale of stars, of compact objects, of distances measured in light years or thousands of light years. The universe is billions of light years across, and on those scales, general relativity has never been tested directly. It has only been assumed. Some theorists suggest that gravity, on cosmological scales, may deviate from what Einstein's equations predict. Not dramatically, the deviations would be subtle, but enough to produce the appearance of accelerating expansion without requiring any new substance at all. In these modified gravity theories, there is no dark energy. There is only gravity, behaving slightly differently than expected when the distances become vast enough. The universe would still be accelerating, The supernovae would still be dimmer than expected. The CMB would still show the same composition, but the cause would not be a mysterious energy-filling space. It would be the geometry of space itself, curving in ways our current equations do not fully capture. Distinguishing this from true dark energy is not simple. It requires measuring not just how fast the universe is expanding, but how quickly structures within it are growing. In a universe with a cosmological constant, structure grows in a specific way. In a universe with modified gravity, it grows differently. The difference is measurable, in principle, with the right instruments and enough data. Current observations are consistent with general relativity. Modified gravity has not been confirmed, but it has not been fully ruled out either. And so it remains another open door, another quiet possibility, in a field full of them. The universe does not make this easy. It offers clues, not answers, constraints, not certainties. It allows us to narrow the space of what is possible, slowly, carefully, over generations of observation. And somewhere in that narrowing space, between the cosmological constant and quintessence, between true dark energy and modified gravity, between what we can measure and what we cannot yet name, the truth is waiting. Patient as the expansion itself. And so the search continues. Not with urgency, but with patience. The kind of patience that only comes from studying something that has been here for billions of years and will remain long after every instrument we have built has gone quiet. One of the most active fronts in that search involves galaxy clusters. These are the largest gravitationally bound structures in the universe, collections of hundreds or thousands of galaxies, held together by gravity, suspended in vast clouds of hot gas. They are, in a sense, the universe's heaviest objects. And because dark energy works against gravity, slowly loosening its hold on the largest scales, the number of clusters that form, and when they form, carries a record of dark energy's influence written into it. If dark energy is strong, it suppresses the growth of structure. Fewer massive clusters form. They form later. They are less dense. If dark energy is weaker or absent, gravity runs unchecked. Clusters grow larger, earlier, more numerous. Counting clusters carefully across cosmic time is one way to read that record. Two instruments have been doing exactly this from opposite ends of the Earth. The South Pole Telescope, built on the Antarctic Plateau where the air is cold and dry and almost perfectly still, scans the sky for a subtle signal. The Atacama Cosmology Telescope, perched high in the Chilean desert at an altitude where the atmosphere is thin enough to be nearly transparent, does the same. Both are searching for what is called the Sunyaev-Zeldovich effect. It is a quiet phenomenon, almost imperceptible, but it is real, and it is measurable. When photons from the cosmic microwave background, that ancient light, traveling since the universe was only 380,000 years old, pass through a galaxy cluster, they encounter the hot gas that fills the space between the cluster's galaxies. That gas is extraordinarily hot, tens of millions of degrees, and as the CMB photons pass through it, they gain a small amount of energy from the electrons in that gas. Their wavelengths shift ever so slightly. The result is a faint distortion in the microwave background, a shadow, in a sense, cast by the cluster's heat. This distortion can be detected from Earth even when the cluster itself is too distant and too faint to be seen directly. It is a way of finding galaxy clusters not by their light, but by the mark they leave on older light passing through them. And because this effect does not depend on how far away the cluster is, only on how much hot gas the photons pass through, it allows astronomers to find clusters across vast stretches of cosmic distance. Clusters that formed when the universe was half its current age, a third of its current age, even younger. By counting how many clusters exist at each distance, each moment in cosmic history, astronomers can trace how structure has grown over time. And that growth curve is sensitive to dark energy. The results, so far, are consistent with the lambda CDM model. The number of massive clusters observed matches what the cosmological constant predicts, with a consistency that is, in its quiet way, remarkable. The universe, it seems, has been suppressing its own structure at roughly the rate we expected. Dark energy has been doing its work. But the story does not end with clusters. Dark energy's influence reaches down to smaller scales as well, not in the dramatic sense of tearing things apart, but in the subtle statistics of how galaxies are shaped by the matter between them. Light bends around mass. This is one of the clearest predictions of general relativity, confirmed a century ago during a solar eclipse. On cosmic scales, the same bending happens continuously, invisibly, as light from distant galaxies passes through the web of matter between them and us. The result is a slight distortion of those galaxies' apparent shapes, a coherent stretching, aligned with the distribution of matter along the line of sight. This is called cosmic shear. No individual galaxy is perfectly round to begin with, so the distortion cannot be seen in any single image. But across millions of galaxies, the distortions align in patterns that reveal the invisible scaffolding of matter they pass through. And because that scaffolding, the cosmic web of filaments and voids, was shaped by the interplay of gravity and dark energy, the patterns of cosmic shear carry dark energy's signature within them. 2 surveys have been measuring this signal with particular care. The Kilodegree survey, which mapped hundreds of square degrees of sky from a telescope in Chile, and the Hypersuprime survey, which did the same from a telescope in Hawaii. Both measured the shapes of hundreds of millions of galaxies. Both extracted the subtle coherence in those shapes. Both attempted to read dark energy's influence from the geometry of distortion written across the sky. The results are informative, and also, in a quiet way, slightly puzzling. When the shear measurements are compared to predictions derived from the cosmic microwave background, from the early universe, before dark energy was dominant, there is a mild tension. The shear data suggests that matter is slightly less clumped than the CMB predicts it should be. The discrepancy is not large. It is not a crisis. It may reflect systematic errors in the measurements, subtle biases in how galaxy shapes are estimated, or how the light is calibrated. Or it may be something else. It may be a hint that dark energy has suppressed the growth of structure slightly more than the standard model expects. That something in the late universe is smoothing things out a little more than lambda CDM predicts. Or it may point toward modified gravity, behaving differently from general relativity on the scales where these measurements are made. The data do not yet say which. And this is, in its way, one of the most honest places in all of cosmology. A place where the measurements are real, the tension is real, and the explanation is genuinely unknown. Not unknown because no one has thought carefully about it. Unknown because the universe has not yet given us enough information to decide. Resolving this tension is one of the central goals of the surveys now being built and launched. The next generation of instruments will measure cosmic shear across areas of sky many times larger than anything attempted before, with more galaxies, better calibration, and sharper images. They will ask the same question with greater precision. Is the universe as clumpy as the early universe predicted it would be? And the answer, whatever it turns out to be, will carry implications for dark energy, for modified gravity, for the cosmological constant, and for the deeper question of whether our current framework is complete. For now, the tension sits quietly in the data. A small discrepancy between 2 measurements of the same universe, made at different times using different methods. It may dissolve when the systematics are better understood. Or it may deepen. And if it deepens, if the next generation of surveys confirms that matter is genuinely less clustered than the early universe predicted, then something in our understanding will need to change. Something about how dark energy behaves, or how gravity works, or how the two interact across the long arc of cosmic time. The universe is patient about revealing this. It has been expanding for 13.8 billion years, It will continue expanding long after every telescope we have ever built has gone cold and dark. The answers are there, written into the geometry of space, the shapes of galaxies, the temperature of ancient light. We are learning to read them. Slowly, carefully, one measurement at a time. And so the work continues. Not in the way science once worked. One astronomer, one telescope, one careful notebook filled by candlelight, but across entire hemispheres of sky, with instruments that never sleep, gathering light from billions of sources at once. The Vera Rubin Observatory sits in the high desert of northern Chile, where the air is thin and the nights are long and dark. Its mirror is wide enough to hold a small house, and every few nights, it will sweep the entire southern sky, not once, but again and again, building a record of how the universe changes over time. The survey it will conduct has a name that carries its own quiet weight: the Legacy Survey of Space and Time. A decade of observations, billions of galaxies tracked across years, thousands of supernovae caught in the act of exploding, their brightness measured, their distances calculated, their light added to the long ledger of cosmic expansion. Each supernova is a data point. Each galaxy's position and shape is a data point. And from the accumulated weight of all of them together, astronomers hope to constrain dark energy's equation of state, that parameter W, the ratio of pressure to energy density, to within a few percent. A few percent after decades of uncertainty. That would be a remarkable precision. And yet, even that may not be enough to tell us what dark energy actually is. This is one of the quieter truths in cosmology. Measuring what something does is not the same as understanding what it is. We can trace the curve of the universe's expansion with extraordinary care. We can pin down W to 3 decimal places. We can map the geometry of space across 10 billion years of history. And still, at the end of all that measurement, the question remains, what is it? The number tells us how dark energy behaves. It does not tell us why space has energy at all. It does not explain where that energy comes from, or why it has the precise value it does, or whether it will remain that value forever. To answer those questions, something deeper is needed. Something that does not yet exist. The two great pillars of modern physics are quantum mechanics and general relativity. Quantum mechanics governs the very small, the behavior of particles, fields, and the fluctuating energy of empty space. General relativity governs the very large, the curvature of space-time, the motion of galaxies, the expansion of the universe. Both theories are extraordinarily successful within their own domains. Both have been tested to remarkable precision, and yet they do not fit together. At the scales where both should apply, the earliest moments of the universe, the interior of black holes, the fundamental nature of space-time itself, the two frameworks give answers that cannot both be right. A complete theory of quantum gravity would reconcile them. It would describe space-time as something that can be quantized, broken into discrete units, woven from something more fundamental than the smooth continuum we currently imagine. That theory does not yet exist, not in a complete and testable form. There are frameworks. String theory imagines that the fundamental constituents of nature are not point particles, but tiny vibrating filaments, existing in more dimensions than we can perceive. Loop quantum gravity proposes that space-time itself is made of discrete loops, a kind of fabric with a minimum grain size. Causal set theory suggests that the deep structure of the universe is a vast network of events, ordered only by cause and effect, with no continuous geometry beneath. Each of these approaches captures something real. Each has produced genuine mathematical insights, and none of them, so far, fully explains dark energy. None dissolves the cosmological constant problem. None tells us why the energy of empty space has the value it does, rather than a value 120 orders of magnitude larger. Some researchers hold a quiet hope that when quantum gravity is finally understood, when the two great frameworks are finally reconciled, the cosmological constant problem will simply disappear, that the answer will emerge naturally from the deeper structure. the way so many puzzles in physics have dissolved when the right language was found. Others are less certain. They suspect that dark energy will remain mysterious even after quantum gravity is understood, that it points towards something beyond both current frameworks, a new way of thinking about space and time and energy, and what it means for something to exist at all. The history of physics offers some comfort here and some humility. Newton's mechanics seemed complete for 2 centuries. Then Maxwell's equations revealed that light was a wave in something, and no one could say what that something was. The resolution required Einstein and a new understanding of space and time that no one had imagined before. Einstein's relativity seemed to explain gravity completely. Then quantum mechanics revealed a world of probability and uncertainty that relativity could not accommodate. The resolution is still being sought. Each time, the mystery was not resolved by gathering more data alone. The data was necessary, but the breakthrough required a new way of seeing, a new set of concepts, a new vocabulary for describing what the universe is made of and how it behaves. Dark energy may be asking for the same thing. It may be the universe's way of telling us that our current concepts, space as a smooth continuum, energy as something fields carry, time as a dimension through which things evolve, are approximations. Useful, extraordinarily precise approximations, but approximations nonetheless. The fact that 95% of the universe is invisible to us, that dark matter and dark energy together outweigh everything we have ever seen or touched or measured directly, is a remarkable situation to be in. It is not a failure. Science has not fallen short. It has succeeded well enough to discover the boundaries of its own understanding, to map the shape of its own ignorance with precision. That is not a small achievement. It is, in its way, a kind of triumph. And the 95% that remains unknown is not a wall. It is an opening. Every telescope pointed at the sky tonight is, in part, searching for a clue. The Rubin Observatory, sweeping the southern sky. The Euclid satellite, mapping the geometry of space across billions of light years. The Roman telescope, counting supernovae by the thousands. The great arrays of radio dishes, the X-ray observatories, the instruments that detect the faint distortions of galaxy shapes. All of them are listening, patiently, carefully, in the language of light and geometry and statistical inference, for something the universe is trying to say, something it has been saying, quietly, in the dimness of distant supernovae and the temperature of ancient light, for as long as we have had the instruments to hear it. We are still learning the language, and that is where the science rests tonight, not at an ending, but at a threshold, with better instruments being built, better measurements being planned, better questions being formed. The universe is under no obligation to be understood quickly. It has been expanding for 13.8 billion years. It will continue long after every observatory we have ever built has gone cold and silent. But the questions we are asking now, about the nature of dark energy, about the structure of space-time, about why the universe is the way it is rather than some other way, these are among the deepest questions any mind has ever formed. And they are being asked carefully and without haste by people who spend their nights in high cold places, watching the sky. One measurement at a time. One measurement at a time. And those measurements, taken together, tell a story that has been unfolding for a very long time. The universe has been expanding for 13.8 billion years. For most of that time, gravity was the dominant voice, pulling matter together, slowing the outward rush, shaping the great filaments and walls of the cosmic web. But roughly 5 billion years ago, something shifted. Dark energy crossed a threshold. Its density, spread thin across the vastness of space, finally outweighed the collective pull of all the matter in the universe. And from that moment, the expansion stopped slowing. It began, quietly and without announcement, to accelerate. 5 billion years. That is longer than the Earth has existed, longer than the sun has been burning. Dark energy has been in charge for the entire history of our solar system. And we are only now beginning to understand what that means. In those 5 billion years, it has done its work slowly. It has stretched the threads of the cosmic web, pulling galaxy clusters apart at their edges, widening the great voids between filaments until they span hundreds of millions of light years. It has not destroyed structure, it has isolated it. The clusters that formed when matter was still dominant have stopped growing. They sit now like islands, their gravitational bonds holding them together while the space between them quietly, steadily expands. And yet, here, in this small corner of the universe, we are sheltered from all of that. The Milky Way is bound, tightly, deeply, by the gravity of hundreds of billions of stars and the dark matter woven through them. Dark energy acts on the geometry of space itself, but it cannot overcome a gravitational bond this strong. Our galaxy will not be torn apart, not by dark energy, not ever, as far as we can tell. And we are not alone in that shelter. The Andromeda Galaxy, a great spiral, roughly the same size as our own, lying about 2.5 million light years away, is gravitationally bound to us. It is, in fact, moving toward us. In about 4 billion years, the two galaxies will begin to merge, slowly, over hundreds of millions of years, their stars passing through each other like two clouds of smoke. The Magellanic Clouds, those two small companion galaxies visible from the southern sky, are bound to us as well, orbiting, drifting, held close by gravity's patient grip. This small collection of galaxies, the Milky Way, Andromeda, the Magellanic Clouds, and a few dozen smaller companions, is called the local group. And the local group is, in a sense, our permanent home. Dark energy will never reach inside it. The expansion of space does not pull apart what gravity holds together. But beyond the local group, everything is leaving. Every other galaxy, every other cluster, every other structure in the observable universe is already receding, carried outward by the expansion that dark energy drives. The Virgo cluster, the nearest large cluster of galaxies, a great gathering of more than 1,000 galaxies lying about 50 million light years away, is drifting beyond our gravitational reach. Not quickly, not dramatically, but steadily and without return. There is no force that will bring it back. And over time, the recession will deepen. In a few 100 billion years, a span of time so large it resists any comparison, the night sky, as seen from any world in the Milky Way, will be nearly empty. The stars of our own galaxy will still be there, scattered across the darkness as they are now. But the universe beyond, the great tapestry of galaxies that fills our telescopes tonight, will have faded past the horizon of the observable, carried so far, so fast, that their light can no longer reach us. Not destroyed, simply unreachable. This is not a violent end. It is something quieter than that. A kind of cosmic solitude, settling in over billions of years, the way silence settles into a room after the last sound has faded. The universe will not end. It will simply become very, very still, and very, very alone. Dark energy does not announce itself. There is no particle that carries it, no radiation it emits, no signal any instrument has ever directly recorded. It does not interact with light. It does not leave a trace in any detector we have built or imagined. It passes through everything, everywhere, at all times, without a whisper. What we know of it, we know only by its absence, by the gap between where things are and where gravity alone would have placed them. The supernovae that were dimmer than expected, the expansion that was slower in the past and faster now, the clusters that stopped growing, the voids that kept widening. None of these things, taken alone, would be enough. But together, they trace the outline of something that is not matter, not radiation, not anything we have a prior name for, something that fills all of space and does work as space expands and leaves the universe larger than it has any right to be. We have named it, and the name is, in a way, an admission: dark energy. Dark. because it does not interact with light. Energy, because it has a density and does work on the universe. But the name carries no explanation within it. It is a label placed on a mystery, not a solution to one. In this way, dark energy may be the most philosophical of all physical phenomena. Every other thing we study in physics can be described by what it is. A photon is a quantum of the electromagnetic field. An electron has a charge and a mass and a spin. Even dark matter, invisible as it is, can be described by what it does to the galaxies around it, how it clusters, how it bends light. But dark energy is defined, almost entirely, by what it is not. It is not matter. It is not radiation. It is not anything that clusters or clumps or interacts. It is known only by the shape of its absence, the way a whole is known by the space around it. We do not know if it is a field, slowly evolving across cosmic time. We do not know if it is a fixed property of space itself, woven into the geometry of the universe at the deepest level. We do not know if it is gravity behaving differently than we expect on the largest scales, an illusion born from an incomplete theory. We do not know if it has a name we have not yet invented, a category of thing that does not yet exist in any textbook. These are not small uncertainties. They sit at the center of physics and cosmology, patient and unresolved, waiting for a framework that has not yet been built. And perhaps that is the right place to rest, for now. Not with an answer, but with the shape of the question, held gently, in the quiet. We do not know if dark energy has always been here, present from the very first moment, woven into space before a single particle existed, or whether it arrived later, emerging from some transition in the universe's long history that we have not yet identified. We do not know if it will stay as it is, constant, patient, unchanging, a quiet hum beneath everything, holding its value across all of time, or whether it is slowly shifting, the way a tide moves so gradually that no single wave reveals the direction. It might grow stronger, pressing outward with increasing force until the structure's gravity has spent billions of years assembling begin, one by one, to come undone. Galaxy clusters first, their bonds stretched past breaking, then galaxies themselves, their stars scattered into the dark, then smaller things, and smaller still, until even the atoms that make up everything you have ever touched are pulled apart at their seams. Or it might fade, quietly diminishing over trillions of years, handing the universe back to gravity, to whatever slow collapse or stillness follows. We do not know which of these is true. We may not know for a very long time. And so we return to what we do know. The universe is larger than it should be. If you trace the expansion backward, accounting only for matter and radiation, and the pull of gravity between them, the numbers do not add up. The universe has stretched further than gravity alone could explain. The galaxies are further apart than they have any right to be. Something pushed them. Something is still pushing. We have measured it as carefully as we can through the dimness of distant supernovae and the faint temperature patterns of ancient light and the spacing of galaxies across hundreds of millions of light years. We have triangulated its presence from every angle available to us. And we have given it a name: dark energy. Two words that describe, with some precision, what we do not understand. The name is not an explanation. It is a placeholder, a label on an empty jar. It tells us where the mystery lives, but nothing about what the mystery is. The name is all we have. And yet, in the quiet of the night, lying still, breathing slowly, that mystery does not feel like a threat. It feels like the universe simply being what it is, vast and old and largely unknown, going about its business with complete indifference to whether we have named it correctly. There is something restful in that. The universe does not need our understanding to continue. It expanded before we were here to measure it. It will expand long after every instrument we have ever built has gone cold and dark. Our equations are approximations of something that was never waiting for us to arrive. And still, we are here. You are here. Every atom in your body was made inside a star. The carbon in your cells, the iron in your blood, the calcium in your bones, each one was forged in the interior of a sun that lived and died before this planet existed. Those atoms drifted through space for millions of years before gravity gathered them, slowly into the world you were born on. But those stars only existed because dark energy was weak enough to allow them. If the cosmological constant had been even slightly larger, not enormously larger, just a little, the universe would have expanded too quickly for gravity to gather anything. Clouds of hydrogen would have dispersed before they could collapse. No stars would have ignited. No heavier elements would have been made. The universe would have been a thin, cold mist, spreading forever into silence. And if dark energy had been absent, or too weak, the story might have ended differently too. Gravity, unopposed, might have drawn everything back together long before stars had time to live and die and scatter their contents across space. The value that dark energy holds, that extraordinarily small number, roughly 6 times 10 to the negative 27 kilograms per cubic meter, sits in a narrow range. A range that permits stars, that permits planets, that permits, after billions of years of slow chemistry and deep time, something like awareness. Whether that precision is a coincidence, or a selection effect, or evidence of something we do not yet have words for, that question remains open. But the fact itself is not in question. The cosmological constant, whatever it is calibrated in a way that made all of this possible. Every star you have ever seen in the night sky, every element in the periodic table heavier than hydrogen, every living thing that has ever existed on this world, all of it traces back, in some quiet and indirect way, to a number that describes the energy density of empty space, a number we cannot yet explain. That is not a small thing to carry into sleep. The knowledge that the universe was arranged, somehow, in just the way that allowed you to exist, not by intention, as far as we can tell, not by design, in any sense we can confirm, but arranged, nonetheless, the constants holding their values, the forces balanced as they are, the expansion proceeding at the rate it does, and here you are, made of ancient stars, lying in the dark, on a planet held in orbit by a star that will burn for another 5 billion years, in a galaxy bound tightly enough by its own gravity that dark energy will never reach inside it, in a universe that has been expanding for 13.8 billion years and will continue expanding quietly, long after every story anyone has ever told has been forgotten. The mystery of dark energy is not frightening. It is simply the outermost edge of what we know. Beyond it, there is more universe, more time, more questions that no one has yet thought to ask. And for now, that is enough. The breath slows. The body settles. Somewhere, 100 billion galaxies are drifting apart, each one carried gently outward by the expansion of space, each one unaware of the others, each one surrounded by a growing darkness that is not empty, but full of something we have not yet named. And here, in this small corner of one ordinary galaxy, everything is still.